Hello and welcome to Kudo Weekly. I'm your host Johan Bontes, and today I want to talk about copying data on the GPU. You may have noticed that there isn't a function called memcopy that you can call device side. So let's fix this and see what options we have to make this as efficient as possible. Let me set up some memcopy example on the device so we have something to talk about. Okay, here we are. Let me walk you through the code to start with. We have a copy function that takes a destination and a source and a size. We then calculate how many times we need to loop around, and we assign each thread a element and copy that from the source into the destination. That's a device function. The global function repeats this whole circus 5 times in order for the times to stabilize. It casts the data1 and data2 to a t-pointer and passes the size. We synchronize afterwards so that all threads have arrived at the point and we can safely take the clock. And then we print out the time. Now for completeness, we should really make this thing volatile, and that one as well, to prevent the optimizer from moving these things around. Now we call this thing 4 times, once with a size of int, 4 bytes, once with a size of int64, and once with a size of int4, which is really 4 ints in a row. And you can see this in the printout. Here we have a size 4. This takes about 4,000 cycles for 1,000 ints, so 1 cycle per byte. If we double the size, the time more or less halves. Then if we double the size again, the size halves again. Well, that's pretty nice. So what would happen if we double the size again? Let's try out. If we double the size again into 8 ints, we get a slightly faster time, but you can see we're running into diminishing returns. And if we were to double that again, we actually don't get any faster anymore. Yeah, a little bit faster, but not a lot. So you can see we're clearly running into diminishing returns. Let's see what happens on the assembly side of things. Now, obviously, it will create a routine for each size. So here we have 16. Now I want to go to the int first. So here we can see the load from memory. Here we have the store to memory, and then we have a whole bunch of loop overhead. Now the loads happen on a int by int basis. Okay, let's have a look at the next function, the one that takes int 64s. Here we are, int long. Now there you can see the load goes by 64 bits, say 64-bit load, and followed by a 64-bit store and some loop overhead. So here we halve the loop overhead and we double the size, which translates into, well, roughly half the size. For the int4, predictably, we load 128 bytes, and then we store 128 bytes. So again, the size of the elements that we've used doubles. When we double the size again, we can see that something different happens. Here, the assembler sees this array here as a range of integers. So it does a whole bunch of integer sized stores. It takes up more instructions, which doesn't sound like the most optimal solution. So perhaps we can tweak this a little bit so that it will take bigger ints. So let's do this an int 4, and let's divide this count by 4 and see if that improves the times. Here we are. Now let's run through the times again. 4 for the int, 2 for the int64, 1, 11, 1.1 for the bigger ones. The other ones have now gone a little bit faster. You see, here we were on 8, and now we're 6, 6.5, and here we get to 4.5. So that definitely helped. And we seem to be, well, running into much better times than before. However, obviously, we are copying 64 bytes times 32. So that is 2K per loop iteration, which means that our data structure better be a multiple of 2K in size. Otherwise, well, we're going to get protection errors because we're running past the end of the array. The solution for that is simply to allocate a bigger size so that it's a multiple of our copy size. The reason why int4 is so efficient at moving data around, why it's such a good chunk size, is a little bit technical. I'll see if I can explain it. On modern processors, this of course can change in the future. Each warp has 16 integer execution units that's backing it up. Of course, there are 32 threads, but there really are only 16 integer execution cores. This means that when you move int4s around, and int4 is 16 bytes, and we have 16 threads working at any one time, we move 256 bytes in one go, and it happens to be exactly the size of one cache line. Because the other 16 threads that we need to make up the 32 in a warp execute the very next cycle, we move one cache line each cycle. This way you can get one cache line every single clock cycle, which is the maximum speed you can extract from this. The only thing that's messing up this perfect scheme is of course our loop overhead. Now if we knew the size at compile time, we could make it a compile time constant, and then the compiler would unroll this loop here and just issue a continuous line of copy instructions. There are two ways to unroll the loop. We can either increase the block size. We've done that here. We call this test function with different block sizes. Or we can explicitly unroll the loop. So here we call the function with double the block size every time. When we look at a single warp, you can see that the time is about 3.8. When we go down to a 64 block, we have 1.9, 28, 1, 5 to 1 for 1024. So you see that it pretty much doubles every time in a nice predictable pattern. Let's have a look at the unrolling. Now here we just added a for loop that takes the unroll template parameter, which is a compile time constant, and the optimizer will unroll this loop because, it gets rid of these compile time for loops. And look at the times. You can see that here we have 1.9 again, just like above. 1.9 above, yes, that makes sense. And then it halves more than half. That's nice. The second doubling, well, it gets to 5, from 8 to 5. Then we get to 3.73. So we quickly run here into diminishing returns. So the moral of the story is that first try and increase your block size. And then if you still have capacity left in whatever structure that you're copying, then look at manual unrolling. Okay, I would like to leave it here. Thank you for watching, and I'll see you next week.